Hello there, and welcome to a journey that will take you to the strangest, most mysterious places in our entire universe. Tonight, we're going to explore something so powerful, so unbelievably massive, that not even light itself can escape its grip. We're going to discover black holes. Imagine a place where the rules of space and time break down, where gravity becomes so intense that it tears apart everything that comes too close. A place where a spaceship, a planet, even a star could vanish forever, disappearing into darkness. This isn't science fiction. These places are real, and they're scattered throughout our galaxy and beyond. Some are far away, safely distant from our home. But did you know there's a supermassive black hole right at the heart of our own Milky Way galaxy? Don't worry, though. We're far enough away that we're perfectly safe, orbiting peacefully around it, along with billions of stars. So get comfortable, relax, and let your imagination drift among the stars. We're about to explore one of the universe's greatest mysteries, and by the end of our journey tonight, you'll understand these cosmic giants in ways that even scientists are still discovering. Let's begin our voyage into the darkness. What exactly is a black hole? The simplest way to think about it is this. A black hole is a place in space where gravity has become so incredibly strong that nothing, not even light, can escape from it. That's why we call it a black hole. It's black because no light can come out for us to see. It's like the universe's ultimate trapdoor, and once something falls in, it can never come back out. Now, you might be wondering, how is that even possible? To understand this, we need to talk about gravity. Gravity is the force that keeps your feet on the ground, that makes a ball fall when you drop it, and that keeps the moon orbiting around Earth. Every object in the universe that has mass creates gravity. The more mass something has, the stronger its gravitational pull. Earth has enough mass to keep you on its surface. The Sun has so much more mass than Earth that its gravity holds our entire solar system together, keeping all the planets in their orbits. But black holes? They take this to an extreme that's hard to imagine. A black hole packs an enormous amount of mass into an incredibly tiny space. Imagine taking something with the mass of several suns and squeezing it down to a point smaller than an atom. The gravity created by this compressed mass is so powerful that it warps and bends the very fabric of space and time around it. Here's something amazing to think about. Black holes don't actually suck things in like a vacuum cleaner, even though many people imagine them that way. If you were far enough away from a black hole, you could orbit around it just like Earth orbits the Sun. The dangerous part is getting too close. There's an invisible boundary around every black hole called the event horizon, and if you cross that line, there's no coming back. The event horizon is like a one-way door. You can go in, but you can never go out. The event horizon got its name because once you cross it, events that happen to you can never be seen or known by anyone outside. It's as if you've left the universe entirely. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers across. That's less than 2 miles. All that mass, compressed into such a small area, creates gravity so intense that even light traveling at 300,000 kilometers per second can't escape. Let's talk about how black holes are born, because understanding where they come from helps us understand what they really are. Most black holes start their lives as massive stars. You see, stars aren't eternal. They're born, they live for millions or billions of years, and eventually they die. How a star dies depends on how massive it is. Stars spend most of their lives in a constant battle between two forces. In the star's core, nuclear fusion creates enormous outward pressure as hydrogen atoms smash together to form helium, releasing tremendous energy. This is what makes stars shine. But at the same time, the star's own gravity is pulling all that material inward, trying to collapse it. For most of a star's life, these two forces balance each other perfectly. But here's the thing, stars don't burn forever. Eventually, a massive star runs out of fuel in its core. When this happens, the outward pressure from fusion can no longer fight against gravity. The core collapses inward in a fraction of a second, falling into itself with incredible force. The outer layers of the star rebound off this collapsed core and explode outward in what we call a supernova, one of the brightest explosions in the universe. A single supernova can briefly outshine an entire galaxy containing billions of stars. But what happens to the core? That depends on how massive the original star was. If the star was 8 times more massive than our sun or smaller, the core becomes something called a white dwarf, a super-dense object about the size of Earth, but containing about as much mass as the sun. If the star was between 8 and about 20 times the sun's mass, the core becomes a neutron star, an object even denser than a white dwarf, where a teaspoon of its material would weigh as much as a mountain on Earth. But if the star was more than about 20 times the mass of the sun, something truly remarkable happens. The core collapses, and nothing can stop it. The gravity is so strong that the core keeps collapsing, crushing down past the neutron star stage, past any point where matter as we know it can resist. It collapses into an infinitely small point called a singularity, wrapped in an event horizon. A black hole is born. This entire process, from the start of the collapse to the formation of a black hole, takes less than a second. One moment there's a massive stellar core. The next moment, there's a black hole, usually with a mass anywhere from about 3 to 50 times the mass of our sun. These black holes are called stellar mass black holes, and scientists think there might be millions of them scattered throughout our galaxy alone. But stellar mass black holes aren't the only kind. In fact, there are several different types of black holes, classified mainly by how much mass they contain. Besides stellar mass black holes, which form from dying stars, there are supermassive black holes. These are the giants of the black hole family, containing anywhere from hundreds of thousands to billions of times the mass of the sun. Almost every large galaxy in the universe has a supermassive black hole at its center. Our own Milky Way galaxy has a supermassive black hole at its heart. We call it Sagittarius a star, and it has a mass of about 4 million suns. Before you worry, remember that we're about 26,000 light-years away from it, safely orbiting around the galaxy's center. The sun takes about 230 million years to complete one orbit around the galaxy. We're far enough away that the black hole's gravity affects us no more than if those 4 million solar masses were spread out in a cluster of stars. Some supermassive black holes are truly mind-boggling in size. There's a black hole called Ton 618, located in a distant quasar, that has a mass of 66 billion times the mass of the sun. Imagine that, 66 billion suns worth of mass, all compressed into a region smaller than our solar system. Its event horizon would be about 11 times the distance from the sun to Neptune. You could fit our entire solar system inside this black hole's event horizon and still have room to spare. Scientists aren't completely sure how supermassive black holes form. They're too massive to have come from even the biggest stars. It would take an incredibly long time for a stellar mass black hole to grow to millions or billions of solar masses just by eating nearby matter. Some scientists think that supermassive black holes might have formed very early in the universe's history, perhaps from massive clouds of gas collapsing directly into black holes without ever forming stars first. Others think they might have grown from smaller black holes that merged together over billions of years. The truth is, we're still figuring this out. There's also a category called intermediate mass black holes, which fall between stellar mass and supermassive black holes. These would have masses between about 50 and 50,000 times the sun's mass. They're much rarer, and scientists have only recently started finding good evidence that they exist. They might form in dense star clusters where many stars are packed closely together, or from the merger of several smaller black holes. And then there's a theoretical type called primordial black holes. These would have formed in the very early universe, just moments after the Big Bang, from tiny density fluctuations in the fabric of space and time itself. If they exist, they could range from incredibly tiny, smaller than an atom, to very massive. The smallest ones would have evaporated away by now through a process we'll talk about later. Scientists are still searching for evidence of primordial black holes, and they remain one of the mysteries we're trying to solve. Now, not all black holes are the same even within these categories. Black holes can differ in two important ways besides their mass. They can spin, and they can have an electric charge. In reality, most black holes probably spin quite rapidly. This makes sense because the stars they formed from were spinning, and when the core collapses down to a tiny size, the spin speeds up dramatically, just like when an ice skater pulls in their arms and spins faster. A spinning black hole is called a Kerr black hole, named after Roy Kerr, the mathematician who first described them. Spinning black holes are more complex than non-spinning ones. The spinning black hole drags space-time around with it in a process called frame dragging. Imagine space and time as a thick fluid, and the black hole is like a spinning ball in that fluid, creating a whirlpool around itself. Anything near a spinning black hole gets caught in this rotating space-time and is forced to move in the direction of the spin. A rapidly spinning black hole also has a region around it called the ergosphere, located just outside the event horizon. In the ergosphere, space-time is being dragged around so forcefully that nothing can stand still, even if it wanted to. Everything in the ergosphere must orbit in the direction the black hole is spinning. Interestingly, it's theoretically possible to extract energy from a spinning black hole through the ergosphere, using something called the Penrose process. You could drop an object into the ergosphere in just the right way, and it could emerge with more energy than it went in with, stealing a tiny bit of the black hole's rotational energy. Black holes can also theoretically have an electric charge, though most scientists think real black holes are probably electrically neutral. This is because if a black hole had a net positive or negative charge, it would quickly attract opposite charges from space around it, neutralizing itself. A charged, non-spinning black hole is called a Reissner-Nordstrom black hole, and a charged, spinning black hole is called a Kerr-Newman black hole. These are fascinating mathematically, but in the real universe, they're probably quite rare. Now let's return to the event horizon, because it's one of the most important and strangest features of a black hole. The event horizon marks the boundary of no return. It's not a physical surface like the ground or a wall. There's nothing solid there. It's simply the distance from the black hole's center, where the escape velocity equals the speed of light. What's escape velocity? It's the speed you need to reach to escape from a massive object's gravity. On Earth, the escape velocity is about 11 kilometers per second. If you throw a ball upward at less than this speed, it will eventually fall back down. But if you could throw it at 11 kilometers per second or faster, it would escape Earth's gravity and fly off into space. The Moon's escape velocity is lower because the Moon has less mass. The Sun's escape velocity is much higher. For a black hole, at the event horizon, the escape velocity is exactly the speed of light, about 300,000 kilometers per second. Since nothing in the universe can travel faster than light, and light itself can't escape, nothing else can escape either. The event horizon's size depends on the black hole's mass. The more massive the black hole, the larger the event horizon. There's actually a simple formula to calculate the size of a black hole's event horizon. It's called the Schwarzschild radius. For a non-spinning black hole, if you take the black hole's mass, multiply it by 2, then multiply by a number called the gravitational constant, and divide by the speed of light squared, you get the Schwarzschild radius. This is the distance from the center to the event horizon. For a black hole with 1 solar mass, the Schwarzschild radius is about 3 kilometers. For a black hole with 10 solar masses, it's 30 kilometers. Double the mass, and you double the radius. Here's something that might surprise you. The event horizon of a supermassive black hole is much, much larger than that of a stellar mass black hole. But the gravity at the event horizon of a supermassive black hole is actually much weaker than at the event horizon of a small black hole. That sounds backwards, doesn't it? But it's true. The reason is that the event horizon of a supermassive black hole is so far from the center that gravity has had more distance to weaken. Gravity follows what's called an inverse square law. If you double your distance from an object, the gravitational force you feel becomes 4 times weaker. If you triple the distance, it becomes 9 times weaker. A supermassive black hole might have millions of times more mass than a stellar mass black hole, but its event horizon is millions of times farther from its center, so the gravity at that distance is actually relatively gentle. In fact, for a supermassive black hole, you could cross the event horizon without even feeling anything unusual at that exact moment. You wouldn't know you had just passed the point of no return until you tried to turn around and realized you couldn't. For a small stellar mass black hole, on the other hand, the tidal forces at the event horizon are incredibly intense. Tidal forces occur when gravity is different from one location to another. Your feet might be pulled much harder than your head if you're falling in feet first. This difference in gravitational pull would stretch you out in a process that has a wonderfully descriptive name: spaghettification. Spaghettification, also sometimes called the noodle effect, is exactly what it sounds like. As you fall toward a black hole, if you go in feet first, your feet are closer to the black hole than your head. They experience stronger gravity and are pulled harder. At the same time, both sides of your body are pulled toward the black hole's center, squeezing you from the sides. The result is that you get stretched longer and thinner, like a piece of spaghetti. For a stellar mass black hole, spaghettification would begin long before you reach the event horizon. You'd be pulled apart by the tidal forces while you were still outside, able in principle to escape if you had a powerful enough rocket. But for a supermassive black hole, the tidal forces at the event horizon are so much gentler that you could cross it intact, still in one piece, unaware that you just sealed your fate. Of course, as you continued falling inward toward the singularity at the center, the tidal forces would eventually grow strong enough to tear you apart, no matter what size black hole you fell into. One of the strangest things about black holes has to do with time. According to Einstein's theory of general relativity, gravity doesn't just pull on objects, it also warps space and time. The stronger the gravity, the more space and time get bent and distorted. Near a black hole, where gravity is incredibly intense, time behaves in ways that seem impossible. Imagine you're watching a friend fall toward a black hole while you stay safely far away. As your friend gets closer to the event horizon, something very odd happens. From your perspective, watching from a distance, your friend appears to slow down. They fall slower and slower the closer they get. Their movements become sluggish, like a video playing in slow motion. Even light coming from them gets stretched to longer, redder wavelengths in a process called gravitational redshift. As your friend approaches the event horizon, from your point of view, they slow down more and more, becoming redder and dimmer, and they never quite seem to reach the horizon. In fact, from your distant perspective, it would take infinite time for them to cross the event horizon. You would see them frozen at the edge, growing dimmer and redder, fading from view but never actually crossing over. But here's the strange part. From your friend's perspective, nothing like this happens at all. From their point of view, they fall toward and through the event horizon at a perfectly normal speed. They don't feel time slowing down for themselves. They cross the horizon in a finite amount of time. The slowing down of time only happens from the outside observer's perspective. This is gravitational time dilation, and it's one of the weirdest confirmed predictions of Einstein's general relativity. Time dilation doesn't just happen at the event horizon. It happens anywhere there's gravity, but it's only noticeable when gravity is very strong. Clocks on GPS satellites in orbit around Earth actually run very slightly faster than clocks on the ground, because they're farther from Earth's center and experiencing slightly weaker gravity. The difference is tiny, just a few microseconds per day, but it's real, and GPS systems have to account for it to work accurately. Near a black hole, though, time dilation becomes extreme. If you could somehow hover just outside the event horizon of a black hole, and you stayed there for what felt like 1 hour to you, when you moved away and checked your calendar, you might find that years or even centuries had passed in the outside universe. The closer you are to the event horizon, the more extreme this effect becomes. Right at the event horizon, time dilation becomes infinite from an outside observer's perspective. This is why, from the outside, it takes forever to see something cross the horizon. Inside the event horizon, things become even stranger. The roles of space and time actually switch. Outside a black hole, you can move freely through space. You can go forward, backward, left, right, up, or down, but you can only move forward through time. Inside the event horizon, the singularity at the center becomes not a place in space, but a moment in your future. Just as you can't stop moving forward in time outside the black hole, inside the black hole you can't stop moving toward the singularity. It becomes as inevitable as tomorrow. No matter which direction you point your spaceship, you're heading toward the singularity, and you'll reach it in a finite amount of your time. At the very center of a black hole, all the mass is concentrated into something called a singularity. A singularity is a point of infinite density, where all the black hole's mass exists in zero volume. At least, that's what the mathematics of general relativity tells us. But here's the truth. We don't really know what happens at the singularity. Our current theories break down there. General relativity predicts a singularity, but most physicists think this is a sign that we need a better theory, one that combines general relativity with quantum mechanics, the physics of the very small. Quantum mechanics and general relativity are two of the most successful theories in all of physics, but they don't work well together. We need a theory of quantum gravity to truly understand what happens at a singularity. And despite decades of effort by some of the smartest physicists in the world, we don't have one yet. So when we talk about singularities, we're talking about the limits of our current knowledge. There might not actually be a point of infinite density. There might be something else there, something we'll discover when we finally figure out quantum gravity. Some scientists think that at the incredible densities inside a black hole, space and time might become grainy or foamy at the tiniest scales far smaller than an atom. Others think there might be a strange quantum state of matter we've never encountered. Still others explore mathematical ideas about black holes connecting to other universes or other regions of space-time through structures called wormholes. These ideas are highly speculative, but they're exciting possibilities that scientists are investigating. Now, you might think that since nothing can escape a black holes can only grow, never shrink. They eat matter and grow bigger, and that's the end of the story. But remarkably, that's not quite true. In 1974, the brilliant physicist Stephen Hawking discovered something shocking. Black holes can actually evaporate. Hawking found that when you apply the rules of quantum mechanics near a black hole's event horizon, something unexpected happens. Quantum mechanics tells us that empty space isn't truly empty. Virtual particles are constantly popping into existence in pairs, a particle and its antiparticle. Normally, these pairs appear for just an instant and then annihilate each other, disappearing back into nothingness. But near a black hole's event horizon, something different can happen. If a particle-antiparticle pair appears right at the edge of the event horizon, one might fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. To conserve energy, the black hole must lose a tiny bit of its mass. This process is called Hawking radiation, and it means black holes very slowly lose mass and energy over time. Don't get too excited, though. For large black holes, Hawking radiation is unimaginably weak. A stellar mass black hole with the mass of our Sun would have a Hawking radiation temperature of only about 1/1000th of a degree above absolute zero. That's much, much colder than the cosmic microwave background radiation left over from the Big Bang, which is about 3 degrees above absolute zero. So stellar mass black holes are actually gaining energy from the universe faster than they lose it through Hawking radiation. They're growing, not shrinking. But here's where it gets interesting. The smaller a black hole is, the hotter its Hawking radiation becomes. A tiny black hole, much smaller than one with a stellar mass, would radiate much more intensely. If a black hole became small enough, it would start evaporating rapidly, getting smaller and hotter, evaporating faster and faster in a runaway process, until finally, in the last fraction of a second, it would explode in a burst of energy. For a black hole with the mass of our Sun, this evaporation process would take an unimaginably long time, about 10 to the 67 years. That's 10 with 67 zeros after it. For perspective, the universe is currently only about 14 billion years old, which is about 10 to the 10th years. So we're talking about timescales trillions upon trillions of times longer than the current age of the universe. But eventually, if the universe lasts long enough, even the largest supermassive black holes will evaporate away to nothing. Only very small black holes would evaporate quickly. A black hole with the mass of a mountain might evaporate in less than the current age of the universe. Any primordial black holes that formed in the early universe and had masses less than about 10 to the 15 grams, about the mass of a mountain, would have already evaporated by now. Some scientists have looked for signs of tiny black holes evaporating but haven't found any yet. If they do, it would be an incredible discovery and would tell us something important about the very early universe. The discovery of Hawking radiation was revolutionary because it connected black holes to thermodynamics, the study of heat and energy. Hawking showed that black holes have temperature and entropy, properties we usually associate with ordinary matter. This suggested a deep connection between gravity, quantum mechanics, and thermodynamics, and it led to many profound questions about the nature of information and reality itself. One of these questions is called the black hole information paradox. Quantum mechanics tells us that information can never be truly destroyed. If you know everything about a system right now, the laws of physics allow you to figure out what it was like in the past or predict what it will be like in the future. Information is preserved. But what happens when something falls into a black hole? The information about that object seems to be lost forever behind the event horizon, hidden from the outside universe. And if the black hole eventually evaporates through Hawking radiation, where does that information go? Hawking radiation, in Hawking's original calculation, is purely random thermal radiation, containing no information about what fell into the black hole. So it seems like information is destroyed, contradicting quantum mechanics. This is the information paradox, and physicists have been arguing about it for decades. Some scientists think information is indeed lost, and we need to modify quantum mechanics. Others think information is somehow encoded in the Hawking radiation in a way we don't yet understand. Still others think information might be preserved in some structure at the event horizon or in subtle correlations in the radiation. Recent work suggests that information might start coming out in the Hawking radiation once the black hole has evaporated about halfway, but the debate is still ongoing. Solving the information paradox might require that theory of quantum gravity we mentioned earlier. Black holes don't just sit alone in space. Many of them are surrounded by material, gas, dust, and even whole stars that have ventured too close. When material starts falling toward a black hole, it doesn't usually fall straight in. Due to conservation of angular momentum, the material has some rotation, some sideways motion. As it falls, it spirals inward, forming a disk around the black hole called an accretion disk. Accretion disks are incredibly hot and bright. As material in the disk spirals inward, particles rub against each other, creating friction. This friction heats the disk to tremendous temperatures, sometimes millions of degrees. At these temperatures, the disk glows brightly, emitting intense light in visible wavelengths, ultraviolet light, X-rays, and even gamma rays, the most energetic form of light. In fact, the brightest continuous sources of light in the universe are supermassive black holes with massive accretion disks. We call these objects quasars when they're especially bright, and they can outshine entire galaxies. It might seem strange that a black hole, which by definition can't emit light, can be associated with some of the brightest objects in the universe. But it makes sense when you realize that the light isn't coming from inside the event horizon. It's coming from the accretion disk outside the black hole. The black hole itself remains dark, but the material swirling around it, heated by friction and the black hole's intense gravity, blazes with brilliant light. Accretion disks don't just glow with light. They also launch powerful jets of particles and radiation from near the black hole's poles. These jets are among the most powerful phenomena in the universe, shooting out material at speeds close to the speed of light. The jets can extend for millions of light years, far beyond the galaxy that hosts the black hole. Scientists aren't completely certain how these jets form, but the leading idea involves the black hole's spin and magnetic fields. As material in the accretion disk moves in the intense magnetic fields around a spinning black hole, some of that material gets channeled along the magnetic field lines toward the poles. There, it's accelerated to incredible speeds and shot outward in tight beams. The details are complex and are still being researched, but observations show these jets are real and carry enormous amounts of energy. In fact, astronomers have recently achieved something incredible. They've actually taken pictures of black holes. Well, not exactly the black holes themselves, since they don't emit light, but they've imaged the glowing material immediately around black holes, showing the shadow of the event horizon against the bright accretion disk. In 2019, the Event Horizon Telescope, a network of radio telescopes spread across the entire Earth working together, released the first ever image of a black hole's shadow. The black hole they imaged is the supermassive giant at the center of a galaxy called Messier 87, or M87, located 55 million light-years away. The image showed a bright ring of light surrounding a dark circular shadow. That shadow is the black hole's event horizon, backlit by the glowing accretion disk. The black hole in M87 has a mass of about 6.5 billion times the mass of the Sun, and its event horizon is about 40 billion kilometers across. Even though it's so far away, the Event Horizon Telescope's resolution was so sharp that imaging this black hole was like standing in New York City and photographing an orange sitting on the moon. It was a triumph of technology and international cooperation, and it confirmed that black holes really do exist, just as general relativity predicted. In 2022, the same team released an image of the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius, a star. This one was harder to image because material orbits around it much faster, changing even during the time it takes to gather the data. But the team succeeded, showing another beautiful ring of light around a dark shadow. These images are direct proof of black holes and give scientists a way to test general relativity in one of the most extreme environments imaginable. Black holes also play a role in one of the most exciting recent discoveries in astronomy: gravitational waves. According to general relativity, massive objects moving through space create ripples in the fabric of space-time itself, like ripples spreading across a pond when you drop a stone in the water. These ripples are called gravitational waves, and they travel at the speed of light. For decades, gravitational waves were only a theoretical prediction. They were too weak to detect. But in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection of gravitational waves. And their source? Two black holes, each about 30 times the mass of the Sun, spiraling around each other and finally merging into a single larger black hole. This collision happened about 1.3 billion years ago in a galaxy far, far away. The two black holes orbited each other closer and closer, moving faster and faster, until in the final moments they were whipping around each other at half the speed of light. When they merged, about 3 solar masses worth of energy was released as gravitational waves in a fraction of a second. That's more power than all the stars in the observable universe combined were putting out at that instant, but released as gravitational waves instead of light. Those waves traveled through space for over 1 billion years, spreading outward in all directions. When they reached Earth in 2015, they caused the entire planet to squash and stretch by an amount smaller than the width of an atomic nucleus. LIGO's incredibly sensitive detectors picked up this tiny signal, and scientists could tell it came from merging black holes by the way the signal increased in frequency and strength, then suddenly stopped, a pattern called a chirp. Since that first detection, LIGO and other detectors have observed hundreds of black hole mergers. Some are stellar mass black holes merging together. Some are mergers between neutron stars, which create black holes if the resulting object is massive enough. Each detection tells us more about how black holes form, how common they are, and how they grow. Gravitational wave astronomy has opened a whole new window on the universe, letting us observe events we could never see with light alone. These mergers also let scientists test general relativity in new ways. After two black holes merge, the resulting black hole vibrates like a ringing bell, settling down into a stable shape. This ring-down phase lasts only a fraction of a second, but gravitational wave detectors can measure it. The vibrations follow patterns predicted by general relativity, and so far, every merger we've observed matches Einstein's theory perfectly. Some black holes don't merge calmly. When they come together, they can emit bursts of energy in other ways too. If the merging black holes have accretion disks or are surrounded by gas, the collision can trigger intense bursts of gamma rays or other radiation. These are some of the most energetic explosions in the universe, briefly visible across billions of light years. Black holes can also grow by tearing apart stars that wander too close. When a star passes within a certain distance of a black hole, the tidal forces can rip the star apart in an event called tidal disruption. The star gets stretched into a long stream of gas. Part of this stream gets flung away into space, but part of it falls back toward the black hole, forming a temporary accretion disk that flares brightly. Astronomers have observed many tidal disruption events, and they provide valuable information about otherwise quiet black holes that aren't actively feeding. The distance at which a star gets disrupted depends on both the star's size and the black hole's mass. For a supermassive black hole, a star might survive much closer to the event horizon before being disrupted than it would near a smaller black hole. In fact, a small star orbiting a supermassive black hole could potentially cross the event horizon intact and be swallowed whole without being torn apart first. Around a stellar mass black hole, though, even a planet-sized object would be shredded long before reaching the horizon. Black holes come in all sizes, exist throughout the universe, and shape galaxies and cosmic evolution in profound ways. At the centers of most large galaxies sit supermassive black holes, and these black holes seem to be connected to the properties of their host galaxies. Galaxies with more massive central bulges tend to have more massive central black holes. It's as if the black hole and the galaxy grow together, each influencing the other's development. One idea is that as a supermassive black hole feeds on gas and grows, the jets and radiation it produces blow away nearby gas, stopping star formation in the central regions of the galaxy. This feedback process might regulate how big galaxies grow. Without it, galaxies might form stars too quickly and look very different than they do. So black holes, despite being tiny compared to galaxies, might play a crucial role in determining what galaxies look like. Black holes don't exist in isolation. Many of them interact with companion objects, and these interactions reveal their presence even though the black holes themselves are invisible. Some of the strongest evidence we have for black holes comes from systems where a visible star orbits an invisible companion. We call these binary systems, and they've taught us an enormous amount about black holes. Imagine two stars born together, orbiting each other in a cosmic dance. If one is massive enough, it will die first, exploding as a supernova and leaving behind a black hole. The other star continues to orbit what's now an invisible partner. From our perspective on Earth, we can watch that visible star moving in an orbit around seemingly empty space. By measuring how fast it moves and the shape of its orbit, we can calculate the mass of the invisible companion. If that mass is more than about 3 times the mass of the Sun, and yet nothing visible is there, we found excellent evidence for a black hole. One of the most famous black hole candidates discovered this way is called Cygnus X1, located about 6,000 light-years from Earth in the constellation Cygnus the Swan. Astronomers discovered a bright blue supergiant star orbiting an invisible companion every 5.5 days. The companion has a mass of about 15 times the Sun's mass. That's far too massive to be a white dwarf or a neutron star. It must be a black hole. Cygnus X1 also emits powerful X-rays, which is another clue. The X-rays come from material being pulled off the visible star and heated to millions of degrees as it spirals into the black hole's accretion disk. Binary systems like this are X-ray bright because the black hole is actively feeding. Gas from the companion star flows toward the black hole, forming that superheated accretion disk we talked about earlier. The disk glows brilliantly in X-rays, which is how we detected Cygnus X1 in the first place. X-ray telescopes in space have found dozens of these X-ray binary systems, each one containing either a neutron star or a black hole stealing material from a normal star. Sometimes the feeding process isn't steady. Material might flow onto the black hole in bursts, causing the system to flare suddenly in brightness. These outbursts can last weeks or months before fading again. Astronomers monitor these systems carefully, learning about how matter behaves under such extreme conditions. Every observation teaches us something new about gravity, about matter, and about black holes themselves. Black holes also bend light in fascinating ways. According to Einstein's general relativity, massive objects warp the fabric of spacetime, and light must follow the curves in that fabric. When light from a distant star or galaxy passes close to a massive object like a black hole, the light's path bends. This effect is called gravitational lensing, and it's one of the most beautiful confirmations of Einstein's theory. If a black hole passes almost directly between us and a distant star, the black hole's gravity bends the light from that star around itself. We might see multiple images of the background star, or the star might appear to brighten as more light is focused toward us, like a cosmic magnifying glass. Astronomers have used this technique to actually detect lone black holes wandering through our galaxy. When a black hole drifts in front of a background star, the star briefly brightens in a very specific way, and by measuring how the brightness changes, scientists can determine the mass of the invisible black hole causing the lensing. Gravitational lensing happens on much larger scales too. Galaxy clusters containing trillions of solar masses can lens the light from galaxies billions of light years behind them. The result is spectacular. We see arcs and rings of light, distorted images of distant galaxies stretched and magnified by the intervening mass. Some of these lensed galaxies are so far away that without the magnification from gravitational lensing, we'd never be able to see them at all. Lensing lets us observe galaxies from when the universe was very young, giving us a window into cosmic history. Very close to a black hole, light behaves in even stranger ways. Remember the event horizon, the boundary from which nothing can escape? Just outside the event horizon, at exactly 1.5 times the Schwarzschild radius, there's another special boundary called the photon sphere. At this distance, gravity is so strong that light can actually orbit the black hole. Imagine shining a flashlight while standing at the photon sphere distance. If you aimed the beam perfectly tangent to the sphere, the light would circle around the black hole and come back to hit you in the back of the head. Of course, you couldn't actually stand there, you'd be in free fall, spiraling into the black hole. And the photon sphere orbit is unstable. Any tiny perturbation would cause the light to either spiral inward toward the event horizon or escape outward to infinity. Light can't stay in that orbit for long. But the photon sphere is real, and it plays an important role in how black holes look. When astronomers imaged the supermassive black holes in M87 and in our own Milky Way, the bright ring of light they saw comes partly from the photon sphere. Light from the accretion disk gets bent around the black hole, orbiting once, twice, or even more times before escaping to reach our telescopes. Each additional orbit creates a fainter ring of light closer to the black hole's shadow. The mathematics of this is beautiful. Each ring is thinner than the previous one by a factor of about 535 times. So the images we see show a bright ring with progressively fainter rings nested inside, all surrounding the dark shadow of the event horizon. This dark shadow in the images isn't exactly the event horizon itself. It's actually about 2.5 times larger than the Schwarzschild radius. This is because light passing close to the event horizon gets captured. even if it starts out slightly farther away. The shadow represents the region from which no light can escape to reach us, and it's one of the most direct pieces of evidence we have that black holes exist exactly as general relativity predicts. Looking at these black hole images, you might notice that one side of the accretion disk appears brighter than the other. This isn't because one side has more material, it's another relativistic effect called Doppler beaming. The disk is spinning at incredible speeds, close to the speed of light in some regions. On the side of the disk that's rotating toward us, the material is moving toward us at these extreme speeds, and its light gets compressed and amplified, making it appear brighter and bluer. On the side rotating away from us, the opposite happens. The light is stretched and dimmed, appearing redder and fainter. This asymmetry in brightness is another confirmation that we're seeing exactly what Einstein's theory predicts. Black holes don't just affect light passing near them. They can also launch some of the most powerful phenomena in the entire universe, relativistic jets. These are narrow beams of particles and radiation shot out from near the black hole's poles at speeds approaching the speed of light. The jets can extend for millions of light years, far beyond the galaxy containing the black hole, visible across vast cosmic distances. How do jets form? The exact mechanism is still being researched, but the leading explanation involves magnetic fields and the black hole's spin. As material in the accretion disk swirls around the black hole, it carries magnetic field lines with it, twisting and amplifying them. These magnetic fields can become incredibly strong. Some of the infalling material gets channeled along these field lines toward the black hole's rotational poles. There, the material is accelerated to nearly the speed of light and shot outward in two opposite directions, creating a pair of jets. These jets carry tremendous energy. A single jet can have the power output of trillions of suns. They plow through the surrounding space, creating huge bubbles and shock waves. In galaxy clusters, jets from supermassive black holes can heat enormous volumes of gas, preventing that gas from cooling and forming stars. In this way, black holes regulate star formation on truly cosmic scales, influencing the evolution of entire galaxies and clusters. When jets point almost directly at Earth, we see incredibly bright sources called blazars. The jet's light is beamed toward us, making the object appear extraordinarily luminous and variable. Blazars can change brightness dramatically over hours or days as instabilities travel down the jet. They're among the most extreme objects we observe, and studying them helps us understand how matter and energy behave at the highest possible speeds and energies. Quasars are another type of extremely bright object, powered by supermassive black holes. The name quasar is short for quasi-stellar radio source, because when they were first discovered in the 1950s, they looked like stars in photographs but emitted strong radio waves. When astronomers measured their distances using the redshift of their light, they were shocked. Quasars are incredibly far away, billions of light years distant, yet they're bright enough to be visible across that immense gulf of space. They must be unimaginably luminous. We now know that quasars are supermassive black holes at the centers of young galaxies, actively feeding on enormous amounts of gas and dust. A typical quasar might consume the equivalent of 100 stars worth of material every year. As this matter spirals into the black hole, it forms a blazing accretion disk that can outshine the entire galaxy containing it. Quasars can be 1,000 times brighter than the Milky Way, which has 200 billion stars. That's the power of a feeding supermassive black hole. Because quasars are so distant and light takes billions of years to reach us from them, we're seeing these objects as they were in the ancient past when the universe was young. The most distant quasars we've found existed when the universe was less than 1 billion years old. Back then, galaxies were forming and merging frequently, providing abundant fuel for growing black holes. Studying quasars gives us a window into the early universe and helps us understand how the first galaxies and black holes formed. As the universe aged and galaxies settled down, most ran out of easily available fuel for their central black holes. The quasar era faded. Today, Most supermassive black holes are quiet, not actively feeding on large amounts of material. Our own Milky Way's central black hole, Sagittarius a star, is relatively quiet. It occasionally flickers in brightness when a blob of gas or an unlucky star gets too close, but most of the time it's dormant. Astronomers think almost all large galaxies went through a bright quasar phase in their youth before settling into quiescence. Black holes also appear in the strangest theoretical predictions of physics. One idea that comes from Einstein's equations is the white hole. While a black hole is a region of space-time you can enter but never leave, a white hole would be the opposite, a region you can never enter, but from which things can emerge. It's like a black hole running in reverse. White holes appear mathematically in the complete solutions to Einstein's equations for non-rotating black holes. These solutions describe not just black holes, but also their time-reversed counterparts. But here's the catch. We've never observed a white hole, and most physicists think they probably don't exist in our universe, at least not in any straightforward way. There's no known physical process that would create one. However, some theoretical physicists think there might be a connection between black holes and white holes through quantum mechanics. When a black hole evaporates via Hawking radiation, some theories suggest it might undergo a quantum transition, transforming into a white hole that explosively releases the information and energy that fell in. This is highly speculative, and the process would take an unimaginably long time. But if it's true, it would resolve some of the paradoxes about black holes and information. Another exotic idea from Einstein's equations is the wormhole, also called an Einstein-Rosen bridge. A wormhole is a hypothetical tunnel through space-time connecting two different locations. You could imagine entering a black hole and emerging from a white hole in a different part of the universe, or even in a different universe entirely. Wormholes are mathematically possible solutions to general relativity, but actually creating or maintaining one would require something called exotic matter, which has negative energy density. We don't know if such matter exists. Even if wormholes exist, they'd likely be incredibly unstable, collapsing almost instantly unless they were somehow held open. Anything trying to pass through might be destroyed by intense tidal forces, or the wormhole might pinch off before you could get through. Despite these challenges, physicists study wormholes because they connect to deep questions in physics. Recent work suggests a surprising link between wormholes and quantum entanglement, that spooky connection between particles that Einstein himself found troubling. Some physicists think that quantum entanglement and wormholes might actually be two ways of describing the same phenomenon. This idea, sometimes called ER equals EPR, could eventually help us understand how spacetime itself emerges from quantum mechanics. These are the frontiers of our knowledge, places where our best theories hint at possibilities but can't yet give definitive answers. That's what makes black holes so exciting. They're not just fascinating objects, they're laboratories for testing physics at its most extreme, where gravity is strongest, where space-time is most warped, and where the quantum and the cosmic meet. Let's think about what would happen if you actually fell into a black hole. We touched on this earlier, but let's explore it more deeply. Your experience would depend a lot on the size of the black hole. For a stellar mass black hole, the tidal forces would tear you apart long before you reach the event horizon. Remember spaghettification. Your feet, being closer to the black hole than your head, would feel much stronger gravity. The difference in force would stretch you thinner and thinner. At the same time, both sides of your body would be pulled toward the black hole's center, squeezing you from the sides. You'd be elongated and compressed simultaneously, stretched into a long, thin strand like spaghetti, hence the name. This wouldn't be gentle. The forces would rip apart the molecular bonds holding your body together, then the atomic bonds, breaking you down into your constituent particles. By the time your remains crossed the event horizon, you'd be a stream of subatomic particles spiraling into the black hole. Not a pleasant thought, but that's the reality of the immense tidal forces near a small black hole. But for a supermassive black hole, like the ones at galaxy centers, the story is quite different. Because these black holes are so much larger, the tidal forces at the event horizon are surprisingly gentle. You could cross the event horizon intact, without even feeling anything unusual at that particular moment. In fact, according to the theory, there's no local way to know you've crossed it. Space around you would look normal. You could see stars in all directions. Light from outside could still reach you. But here's the terrifying part. You've still crossed the point of no return. Once inside the event horizon, your future is sealed. All paths, no matter which direction you try to go, lead toward the singularity at the center. It's not that you're being pulled toward it exactly. It's that the singularity has become a moment in your inevitable future, as unavoidable as tomorrow. As you fall inward, the tidal forces would gradually increase. Eventually, they'd grow strong enough to start pulling you apart, just like with the smaller black hole, but it would happen deeper inside, closer to the singularity. In your final moments, you'd be stretched and compressed, broken down into elementary particles, and finally absorbed into the singularity itself. From your perspective, this entire journey from crossing the event horizon to reaching the singularity might take only seconds or minutes. But remember time dilation. To someone watching from outside, they'd never see you cross the horizon. To them, you'd appear to slow down more and more, becoming redder and dimmer, frozen forever at the edge. They'd see you fade from view, but never actually enter. This difference in perspectives is one of the strangest features of black holes, a direct consequence of how gravity warps time. Inside the event horizon, space-time is so severely warped that the direction toward the singularity becomes time-like, while the direction around it becomes space-like. In normal space, you can move freely in the three spatial directions, but only forward in time. Inside a black hole, this reverses. The radial direction toward the singularity becomes like time, inexorably moving forward, while the angular directions become like space, where you have some freedom to move. But just as you can't stop time from passing outside the black hole, you can't stop yourself from reaching the singularity once you're inside. What would you see as you fell? That's another fascinating question. Due to the extreme warping of light paths, you'd see bizarre optical effects. Light from outside the black hole would be compressed into a shrinking circle behind you, blue-shifted and intensely bright. The rest of your view would be dominated by darkness or by distorted, multiple images of objects near the black hole. If there were other objects falling in with you or orbiting nearby, you might see them in strange, warped configurations, their images stretched and repeated. There's also a theoretical possibility, though highly speculative, that you might see something unexpected at the singularity. Some theories suggest that instead of a point of infinite density, there might be a quantum structure, or a transition to a different space-time region, or even a connection to another universe. We simply don't know. Our current physics breaks down at singularities, and we need a theory of quantum gravity to truly understand what's there. Until we develop that theory, the inner workings of black holes remain mysterious. Black holes can also collide with each other. When two black holes orbit close together, they lose energy by emitting gravitational waves. This causes their orbits to decay, bringing them closer and closer together in a process called in spiral. They circle each other faster and faster, eventually whipping around at significant fractions of the speed of light before finally merging into a single, larger black hole. During the final moments of this merger, the two event horizons touch and stretch, forming a brief bridge between them before blending into one. The newly formed black hole is violently distorted, wobbling and oscillating as it settles down into a stable shape. This settling down process, called ringdown, emits a final burst of gravitational waves, like the fading ring of a bell that's been struck. The gravitational waves from these mergers travel outward through the universe at the speed of light, carrying information about the masses and spins of the black holes and the properties of the final merged object. When these waves pass through Earth, they cause space itself to stretch and compress by tiny amounts. LIGO and other gravitational wave detectors measure these minute distortions, revealing details about events that happened millions or billions of years ago in distant corners of the cosmos. Some black hole mergers are truly extreme. When two supermassive black holes merge, for example at the end of a galactic merger, the energy released can be staggering. If the two black holes have unequal masses or spins, the merger can be asymmetric, releasing more gravitational waves in one direction than others. This creates a recoil, a kick that can send the resulting black hole speeding through space at hundreds or even thousands of kilometers per second. Some merger kicks are powerful enough to eject the black hole from its host galaxy entirely, sending it wandering through intergalactic space. Astronomers have found evidence of recoiling supermassive black holes, objects moving at high speeds relative to their host galaxies. These provide more confirmation that black hole mergers really do happen, and that the gravitational wave emission is asymmetric just as predicted. Each discovery adds another piece to our understanding of these extreme cosmic events. Black holes have captivated scientists and the public alike for decades, but much of what we know has been discovered only recently. The first black hole candidates were identified in the 1970s. Hawking radiation was predicted in 1974. The first gravitational wave detection happened in 2015. The first black hole image was released in 2019. We're living in a golden age of black hole science, where theory and observation finally meet, confirming predictions made decades ago and revealing new mysteries to solve. For example, in 2025, scientists confirmed through observations that the area of a black hole's event horizon never decreases, a prediction made by Stephen Hawking called the area theorem. By analyzing the gravitational waves from a black hole merger, they showed that the total area of the two original black holes was indeed less than the area of the final merged black hole, just as Hawking's theorem required. This was a beautiful vindication of theoretical work done 50 years earlier. Scientists have also begun discovering intermediate mass black holes, those mysterious objects between stellar mass and supermassive. For years, these were mostly missing from observations, but new techniques and instruments are finding them in dense star clusters and in some smaller galaxies. Each discovery helps fill in the picture of how black holes form and grow across different environments and epochs of cosmic history. We're also learning that black holes might not be as isolated as we once thought. The centers of galaxies are complex environments, and supermassive black holes interact with their surroundings in subtle ways. The gas and stars near a black hole move in orbits influenced by the black hole's gravity, but also by the gravity of other nearby stars and gas clouds. These interactions create complex dynamics that can feed the black hole episodically, causing periodic outbursts of activity. One example is a system called OJ-287, which shows periodic brightness variations every 12 years. Astronomers believe this system contains two supermassive black holes orbiting each other. The smaller black hole periodically plunges through the accretion disk of the larger one, creating a burst of light each time. By carefully timing these bursts, scientists can test general relativity with extreme precision, because the orbit's evolution depends on subtle relativistic effects. Black holes also play a role in the chemical evolution of galaxies. When stars form, live, and die near a black hole, the elements they produce can be expelled by supernova explosions or by jets from the black hole itself. These elements enrich the surrounding gas, which eventually forms new generations of stars. In this way, the cycle of stellar birth and death near black holes contributes to the growing complexity of matter in the universe, forging heavier elements that are essential for planets and life. Even the event horizon itself might be more complex than we thought. Some theories suggest that the horizon isn't perfectly smooth, but might have structure at quantum scales. There's an idea called the black hole firewall paradox, which suggests that if information is preserved in black hole evaporation, there might be a wall of high-energy particles right at the event horizon. This contradicts the idea that nothing special happens at the horizon, and physicists are still debating how to resolve this paradox. The answer likely lies in a complete theory of quantum gravity. These puzzles and questions are what make black holes such a vibrant area of research. They're places where our understanding is pushed to its limits, where we confront the deepest mysteries of space, time, matter, and information. Every new observation and every new theoretical insight brings us closer to a complete understanding, but also reveals new questions we hadn't thought to ask. Black holes are more than just cosmic vacuum cleaners or holes in space. They're actually connected to some of the deepest laws of nature, laws that govern everything from how engines work to why ice cubes melt in warm water. These laws are called thermodynamics, and remarkably, black holes follow their own version of these same rules. In the early 1970s, a physicist named Jacob Bekenstein made a surprising discovery. He realized that black holes have something called entropy. Entropy is a measure of disorder or randomness in a system. When your bedroom gets messy, its entropy increases. When ice melts into water, entropy increases because the water molecules are more randomly arranged than they were in the ice crystal. The second law of thermodynamics says that entropy in a closed system always increases over time. Things naturally tend toward more disorder, not less. But black holes seem to violate this law. When you drop something into a black hole, all the information about that object disappears. It's as if you threw away 1,000 puzzle pieces without ever seeing what picture they made. This seemed to decrease the total entropy of the universe, which shouldn't be possible. Bekenstein solved this problem by suggesting that black holes themselves have entropy, and when something falls into a black hole, the black hole's entropy increases enough to make up for the lost entropy of the fallen object. The amazing part is where the black hole's entropy is stored. It's not stored in the volume inside the event horizon. Instead, it's proportional to the area of the event horizon itself. Think about that for a moment. If you have a box and you want to store more information in it, normally you'd need to make the box bigger in all 3 dimensions, increasing its volume. But with black holes, the amount of information is limited by the 2-dimensional area of the surface, not the 3-dimensional volume inside. There's a simple formula for black hole entropy called the Bekenstein-Hawking entropy. It says that the entropy equals the area of the event horizon divided by 4, in special units called Planck units. For a black hole with the mass of our Sun, the entropy is enormous, about 10 to the 54th power. That's 10% followed by 54 zeros. To put that in perspective, all the entropy in all the particles in the entire observable universe is estimated to be around 10 to the 90th power, and most of that is in the cosmic microwave background and in black holes. When Hawking discovered that black holes emit radiation and have a temperature, this connection to thermodynamics became even clearer. Black holes obey laws that are exactly analogous to the laws of thermodynamics. There's even a 0th law, a first law, a second law, and a third law of black hole mechanics, each mirroring the corresponding thermodynamic law. The 0th law says that the surface gravity is constant across the event horizon of a stationary black hole. This is like temperature being constant throughout an object in thermal equilibrium. The first law relates changes in the black hole's mass to changes in its area, angular momentum, and electric charge. It's a statement of energy conservation, just like the first law of thermodynamics. The second law says that the total area of all event horizons in the universe can never decrease. This mirrors the second law of thermodynamics, which says entropy can't decrease. This deep connection between black holes and thermodynamics led to one of the most mind-bending ideas in modern physics, the holographic principle. Remember how a black hole's entropy depends on the area of its event horizon, not its volume? Physicists Leonard Susskind and Gerard 't Hooft realized this might mean something profound about the nature of reality itself. The holographic principle suggests that all the information contained in a 3-dimensional region of space can be encoded on a 2-dimensional surface surrounding that region, like a hologram. You've probably seen holograms before. Those images that look three-dimensional but are actually printed on a flat surface. The holographic principle says the entire universe might work this way. All the information about everything inside a volume of space, all the particles, all their properties, all their interactions, might be encoded on the boundary of that space. This sounds like science fiction, but it's taken very seriously by theoretical physicists. In fact, there's a specific mathematical realization of this idea called the AD-S-CFT correspondence, discovered by physicist Juan Maldacena in 1997. This correspondence shows that certain theories of gravity in a curved space are exactly equivalent to certain quantum theories without gravity in one fewer dimension. It's as if a three-dimensional universe with gravity is secretly the same as a two-dimensional universe without gravity, just described in a different way. If the holographic principle is true, it would mean that the three-dimensional world we experience, the universe filled with galaxies and stars and planets and people, is in some sense a projection from information encoded on a distant two-dimensional surface. We might be living in a hologram without even knowing it. This idea is still being explored and debated, but it represents one of the most promising paths toward understanding quantum gravity, the theory that will eventually replace or extend general relativity at the smallest scales. Let's return to the properties of spinning black holes, because we only touched on them briefly before. When a black hole spins, it doesn't just sit there rotating, it actually drags the fabric of space-time around with it. This effect is called frame dragging, and it's one of the strangest predictions of general relativity. Imagine space-time as a thick fluid, like honey. Now imagine a sphere spinning in that honey. The honey near the sphere gets dragged around, creating a swirling pattern. This is similar to what happens with space-time around a spinning black hole, except space-time isn't really a fluid. It's the very fabric of existence, the stage on which all events take place. Yet it can be twisted and dragged by rotating mass. For a slowly rotating object like Earth, frame dragging is incredibly weak. It was first measured by a satellite called Gravity Probe B, which carried extremely sensitive gyroscopes into orbit around Earth. The satellite measured that Earth's rotation drags space-time by a tiny angle, about 1 part in a few billion, exactly as general relativity predicted. It took 45 years from when the mission was first proposed to when the results were announced, because the effect is so small and the measurements had to be so precise. But around a rapidly spinning black hole, frame dragging becomes extreme. Just outside the event horizon, there's a region called the ergosphere, where the frame dragging is so strong that nothing can remain stationary. Even if you fired your rocket engines at full blast trying to stay still relative to distant stars, you'd be dragged around the black hole in the direction of its spin. It's as if space-time itself is a river rushing past you, and no matter how hard you swim upstream, you're swept along. The ergosphere extends from the event horizon out to a slightly larger radius that depends on the black hole's spin rate. It has an interesting shape, bulging out at the equator and touching the event horizon at the poles. Inside the ergosphere, it's theoretically possible to extract energy from the black hole's rotation using something called a Penrose process, named after physicist Roger Penrose. You could send an object into the ergosphere, split it into 2 parts in just the right way, let one part fall into the black hole while the other escapes, and the escaping part could have more energy than the original object had. You'd be stealing rotational energy from the black hole, slowing its spin very slightly. This might sound like science fiction, but some scientists think it could be related to how jets form around spinning black holes. The twisted magnetic fields in the ergosphere might accelerate particles and extract energy from the black hole's spin, feeding the tremendous power of relativistic jets. Recent observations in 2025 actually confirmed frame dragging around a real black hole for the first time, by measuring how the orbits of nearby stars wobbled in a specific pattern predicted by general relativity. Speaking of real black holes, let's talk about some of the most famous ones that scientists have discovered and studied. The very first object widely accepted to be a black hole was Cygnus X1, discovered in 1964. It's located about 7,000 light-years away in the constellation Cygnus the Swan. Cygnus X1 is what we call an X-ray binary, a system where a normal star orbits a black hole. The visible star in the system is a blue supergiant, a massive star burning bright and hot. It's locked in a close orbit with an invisible companion, completing one orbit every 5.5 days. The two objects are separated by only about 30 million kilometers, which is less than a quarter of the distance from Earth to the Sun. That's incredibly close for such massive objects. The black hole pulls gas off the surface of the supergiant star, and this gas spirals inward, forming a hot accretion disk that glows brilliantly in X-rays. By measuring how fast the visible star orbits, and using Newton's and Einstein's laws of gravity, astronomers calculated that the invisible companion must have a mass of about 21 times the mass of the Sun. That's far too massive to be a white dwarf or a neutron star. It has to be a black hole. Cygnus X1 was so important to our understanding of black holes that Stephen Hawking made a famous bet about it with physicist Kip Thorne in 1975. Hawking bet that Cygnus X1 wasn't actually a black hole. That might sound strange, since Hawking is famous for his work on black holes, but he made the bet as a kind of insurance policy. If black holes didn't exist, at least he'd win the bet and get a consolation prize. But as evidence mounted, Hawking conceded the bet in 1990, and Cygnus X1's status as a black hole became firmly established. An even more important black hole sits right at the center of our own Milky Way galaxy. It's called Sagittarius, a star, and it has a mass of about 4 million times the mass of the Sun. For many years, astronomers suspected it was there because they could see stars orbiting around an invisible point at the galaxy's center. By tracking these stars' motions over many years, they could calculate the mass of the object they were orbiting. One star, called S2, orbits Sagittarius, a star, every 16 years, at speeds up to about 5,000 kilometers per second. That's almost 2% of the speed of light. By measuring S2's orbit precisely, astronomers Andrea Ghez and Reinhard Genzel proved that Sagittarius A star exists and measured its mass. For this work, they were awarded the Nobel Prize in Physics in 2020. In 2022, the Event Horizon Telescope took the first direct image of Sagittarius, a star, showing the bright ring of light from its accretion disk surrounding a dark shadow. It was another triumph for science and for Einstein's theory. Most of the time, Sagittarius A star is relatively quiet. It's not actively feeding on large amounts of material, but occasionally a blob of gas or an unlucky star ventures too close, and the black hole flares in brightness for a few hours or days. Astronomers watch it carefully, learning more about how black holes feed and how their surroundings behave. Now let's explore an idea that sounds like it contradicts everything we've said about black holes: naked singularities. We've talked about how black holes have singularities at their centers, hidden safely behind event horizons where we can never see them. But what if a singularity could exist without an event horizon? What if you could see a singularity directly, naked and exposed? According to Einstein's equations, under certain special conditions, this might be possible. If you have a very rapidly spinning black hole and you add enough angular momentum, or if you have a charged black hole and add enough electric charge, the event horizon might disappear, leaving the singularity exposed. A naked singularity would be a place of infinite density and infinite curvature that we could actually observe. Most physicists think naked singularities probably don't exist in nature, at least not in our universe. This idea is called the cosmic censorship hypothesis, proposed by Roger Penrose in 1969. Cosmic censorship says that nature abhors a naked singularity, that some law of physics we don't fully understand, yet always prevents them from forming. Event horizons are like a cosmic modesty curtain, always hiding singularities from view. Why does this matter? Because singularities are places where our physical theories break down completely. We can't predict what will happen at or near a singularity. If naked singularities existed and we could observe them, we'd see events that can't be predicted by any law of physics we know. The future would become fundamentally unpredictable. This would undermine the very foundation of science, which is based on the idea that the laws of physics allow us to predict what will happen next. Cosmic censorship remains unproven after more than 50 years. Mathematicians and physicists have tried to prove it rigorously, but haven't succeeded. They've also tried to find counterexamples, situations where naked singularities form, but even that has been difficult. Recent work using quantum mechanics suggests that when you include quantum effects, naked singularities might become hidden behind event horizons after all, supporting cosmic censorship. But the final answer isn't known yet. It's one of the deepest open questions in theoretical physics. Black holes aren't just silent objects sitting in space. When they collide, they create one of the most powerful events in the entire universe, and remarkably, we can hear them. Well, not with our ears, but we can convert the gravitational waves they produce into sound waves that our ears can detect. When LIGO detected the first gravitational wave signal from merging black holes in 2015, scientists converted the pattern of the signal into sound. What they heard was a chirp, a rising tone that increased in frequency and loudness before suddenly cutting off. The chirp lasted only a fraction of a second, but it told an incredible story. At the beginning of the chirp, the two black holes were orbiting each other, still separated by hundreds of kilometers, circling each other several times per second. As they lost energy to gravitational waves, they spiraled closer together, orbiting faster and faster. The frequency of the gravitational waves increased, creating the rising pitch of the chirp. In the final moments, the black holes whipped around each other at about half the speed of light, creating waves with frequencies we can hear if we speed them up slightly for our ears. Then, in an instant lasting less than a tenth of a second, the two event horizons touched and merged. The signal abruptly stopped, or rather, it transitioned to a different phase called ringdown, where the newly formed black hole vibrated like a struck bell, settling down into a stable, smooth shape. The ringdown lasted only about 10 milliseconds, creating a final decaying tone. The entire event, from the first detectable waves to the final ringdown, released more energy than all the stars in the observable universe were emitting at that same moment, but it was released as gravitational waves rather than light. Scientists have now detected hundreds of these black hole mergers. Each one sounds slightly different, depending on the masses and spins of the colliding black holes. Some are high-pitched chirps from small black holes. Others are low rumbles from supermassive black holes. Listening to these sounds is like listening to the universe's own music, a cosmic symphony played on instruments of pure spacetime. The ringdown phase is particularly interesting. When the merged black hole vibrates, it creates gravitational waves at specific frequencies determined by its mass and spin, just like a bell creates sound waves at frequencies determined by its size and shape. By analyzing the ringdown, scientists have confirmed predictions made by Roy Kerr in 1963 about how spinning black holes behave. In 2025, they detected multiple frequencies in the ringdown of one black hole merger, like hearing both the fundamental tone and an overtone of a musical instrument. The relationship between these frequencies matched Kerr's predictions exactly, confirming that black holes really can be described by just two numbers, mass and spin. Now let's peer into the far future and explore what happens to black holes over unimaginably long timescales. We live in a young universe, only about 14 billion years old. Stars still shine, galaxies still form. The universe is active and bright, but this is just the beginning of the story. The universe will likely exist for much, much longer than it already has, and its far future will be very different from its present. Current observations suggest the universe will keep expanding forever. Galaxies will drift farther and farther apart. Star formation will continue for perhaps another trillion years, but eventually, the supply of hydrogen gas needed to make new stars will run out. The last stars will flicker out around 100 trillion years from now. The universe will go dark, filled only with stellar remnants, white dwarfs, neutron stars, and black holes. As time goes on, these remnants will slowly fall into the supermassive black holes at the centers of galaxies, or they'll be ejected from galaxies entirely through gravitational interactions. After about 100 quintillion years, most galaxies will have dissolved, leaving isolated black holes wandering through the expanding void. The universe will be cold, dark, and nearly empty. But even black holes don't last forever. Remember Hawking radiation? Black holes very slowly evaporate by emitting particles, losing mass over time. For stellar mass black holes, this process takes an unbelievably long time. A black hole with the mass of the Sun would take about 10 to the 67th years to evaporate completely. That's a 1 followed by 67 zeros. For comparison, the current age of the universe is only about 10 to the 10th years. So we're talking about timescales trillions of trillions of trillions of times longer than the universe has existed so far. Supermassive black holes take even longer to evaporate. The black hole at the center of the Milky Way, with 4 million solar masses, would take about 10 to the 93rd years to evaporate. The largest known black holes, with tens of billions of solar masses, might take 10 to the 100 years or even longer. These timescales are so vast that it's hard to even conceptualize them, but eventually, if the universe lasts long enough, even these cosmic giants will fade away. The Hawking radiation from evaporating black holes will be nearly the only activity in the universe. As a black hole gets smaller, it gets hotter and evaporates faster. In its final moments, a black hole would evaporate explosively, releasing its remaining mass energy in a brilliant flash. But there would be no one around to see it. No stars, no planets, no life. Just empty space scattered with the last fading particles. After all the black holes have evaporated, the universe will reach what's called heat death, or maximum entropy. Everything will be spread out evenly, at the same temperature, very close to absolute zero. No energy will be concentrated anywhere. No stars will shine. No black holes will exist. No processes will happen. The universe will be a vast, cold, dark, unchanging void, filled with nothing but a thin soup of elementary particles and radiation, all at the same temperature, drifting endlessly farther apart as space continues to expand. This might sound depressing, but remember, we're talking about timescales so long that they make the current age of the universe look like the blink of an eye. Humanity, life, stars, even the era of galaxies and black holes are all part of a tiny sliver of time near the very beginning of the universe's existence. In a sense, almost the entire history of the universe will be about black holes. They'll be the dominant objects for the vast majority of cosmic time, slowly evaporating in the darkness, the last guardians of structure and order before everything fades to heat death. But perhaps even this isn't the end. Some physicists speculate about what might happen in the unimaginably distant future, long after heat death. Could quantum fluctuations create new universes? Could the laws of physics themselves change? Could consciousness or information exist in some form we can't imagine? These are questions at the very edge of science, more philosophy than physics at this point, but they remind us that even when we think we understand something, there are always deeper mysteries waiting. Black holes have taught us that the universe is stranger and more wonderful than we ever imagined. They've shown us that space and time are not fixed stages, but flexible fabrics that can be warped and twisted. They've revealed connections between gravity, quantum mechanics, thermodynamics, and information theory that we're still trying to fully understand. They've given us windows into the strongest gravitational fields, the highest densities, and the most extreme conditions that exist in nature. Every black hole is a laboratory for testing Einstein's general relativity in its most extreme regime. Every observation teaches us something new. Every theoretical breakthrough opens new questions. Some scientists wonder if black holes might even be portals to other universes or other times, though these ideas remain highly speculative. Others explore whether the interiors of black holes might harbor entirely new laws of physics, hidden from our view but waiting to be discovered. Some physicists have even wondered whether it might be possible to create artificial black holes in laboratory settings. With our current technology, this is impossible. Creating even the tiniest black hole would require concentrating enormous amounts of energy in an incredibly small space, far beyond what any particle accelerator could achieve. But scientists have created what they call analog black holes, systems that mimic some properties of black holes using flowing water, laser beams, or other materials. These analogs have allowed researchers to study phenomena like Hawking radiation in controlled settings, even though they don't involve actual gravity or actual black holes. In an intriguing experiment in the UK, physicists used optical fibers to create an artificial event horizon for light. By sending pulses of light through the fiber that changed the refractive index, they created a moving boundary that slower light couldn't cross. It was a horizon of sorts, not for space-time, but for light in a medium. While it's not the same as a real black hole, these analog systems let scientists test theoretical predictions and gain insights that might otherwise be impossible to obtain. There's something profound about the fact that black holes, the darkest objects in the universe, have illuminated so much about how nature works at the deepest level. They've connected ideas from different branches of physics in unexpected ways. They've shown us that information, entropy, and gravity are intimately linked. They've pushed the boundaries of mathematics and computation. They've inspired countless scientists, artists, and dreamers to imagine what lies beyond the known. As we continue to study black holes with better telescopes, more sensitive gravitational wave detectors, and more powerful computers running more sophisticated simulations, we'll undoubtedly discover even more surprises. There are questions we haven't even thought to ask yet, mysteries hidden in the mathematics and the observations, waiting for someone to notice them. Let's explore how black holes might have played a role in the very earliest moments of our universe, billions of years before the first stars ever formed. When we look out into space with powerful telescopes, we're also looking back in time, because light takes time to travel across vast distances. The farther away something is, the longer its light has been traveling to reach us, and the further back in time we're seeing it. Using instruments like the James Webb Space Telescope, launched in 2021, astronomers have been peering deeper into the universe's past than ever before. And they found something surprising. Supermassive black holes already existed when the universe was very young, less than 1 billion years after the Big Bang. Some of these ancient black holes already had masses of hundreds of millions or even billions of solar masses. This creates a puzzle. How did these black holes get so big so fast? Remember, the universe was only about 700 million years old when we see some of these giants. That's barely any time at all in cosmic terms. There simply hasn't been enough time for a normal stellar mass black hole formed from a dying star to grow to billions of solar masses by eating nearby gas and stars. Even if it fed constantly at the maximum possible rate, it couldn't have grown that large. One possibility is that these supermassive black holes formed through a different process entirely. Perhaps they didn't start as small stellar mass black holes. Instead, massive clouds of primordial gas, shortly after the Big Bang, might have collapsed directly into very large black holes without ever forming stars first. These would be called direct collapse black holes, and they could have started with masses of thousands or even tens of thousands of times the Sun's mass, giving them a huge head start. Another possibility scientists are exploring is that some black holes formed even earlier, in the very first moments after the Big Bang itself. These would be primordial black holes, and they're one of the most fascinating hypothetical objects in cosmology. In the incredibly hot, dense conditions that existed in the first fraction of a second after the Big Bang, tiny random fluctuations in density might have been enough to create pockets that collapsed into black holes. These primordial black holes could have had any mass, from unimaginably tiny, smaller than an atom but heavier than a mountain, to extremely large. The smallest ones would have evaporated away long ago through Hawking radiation. But larger primordial black holes, if they exist, could still be out there today. And here's where it gets really interesting. They might account for dark matter. Dark matter is one of the biggest mysteries in science. When astronomers measure how fast galaxies spin or how galaxy clusters move, they find that there must be 5 times more matter out there than we can see. All the stars, planets, gas clouds, everything made of ordinary atoms, only accounts for about 20% of the matter in the universe. The other 80% is dark matter, something that doesn't emit, absorb, or reflect light. We only know it's there because of its gravitational effects. For decades, most scientists assumed dark matter must be some kind of exotic particle we haven't discovered yet. Physicists have looked for particles called WIMPs, or weakly interacting massive particles, and axions, and sterile neutrinos. But so far, no one has directly detected any of these proposed dark matter particles, despite years of searching with increasingly sensitive detectors. But what if dark matter isn't a new type of particle at all? What if it's just black holes? Primordial black holes scattered throughout the universe, formed in the first instant after the Big Bang, would be completely invisible. They'd interact with ordinary matter only through gravity. And they wouldn't require any new physics to explain. They're just objects predicted by general relativity that happen to form very early. Recent research has explored this possibility more seriously. In 2024 and 2025, scientists at MIT and other institutions calculated that if primordial black holes formed during a specific phase transition in the early universe, called the QCD transition, which happened about 1/10,000th of a second after the Big Bang, they might have exactly the right properties to explain dark matter. These black holes would have masses around 1 solar mass, about the mass of our Sun, but compressed into a region smaller than an atom. Some scientists even suggest that gravitational wave observations from LIGO might be finding evidence for primordial black holes. When LIGO detects merging black holes with unexpected masses or in unexpected places, it could be seeing primordial black holes colliding, rather than black holes formed from stars. A detection announced in 2025 showed a black hole merger with unusually small masses, consistent with primordial origins. However, other observations have put limits on how many primordial black holes could exist. If there were too many, we'd see more gravitational lensing effects when they pass in front of distant stars. Surveys of nearby galaxies have looked for these brief brightening events and haven't found as many as some theories predicted. So while primordial black holes might account for some dark matter, they probably can't explain all of it. The mystery continues. Whether or not they're dark matter, black holes definitely played a crucial role in shaping the galaxies we see today. There's a remarkable relationship between supermassive black holes and their host galaxies. The mass of a galaxy's central black hole is closely related to properties of the galaxy itself, particularly the mass and velocity of stars in the central bulge. This relationship was discovered in the early 2000s and was quite surprising. Why should a black hole that contains perhaps 1% of a galaxy's total mass be so closely connected to the properties of the entire galaxy? The black hole is tiny compared to the galaxy, yet they seem to have grown together in lockstep. This suggests they must have influenced each other's development through a process called coevolution. Here's how it likely works. When a supermassive black hole feeds actively, creating a quasar or active galactic nucleus, it releases tremendous amounts of energy. Some of this energy goes into heating the gas in and around the galaxy. Jets and winds from the black hole can push gas out of the galaxy entirely, or at least keep it so hot that it can't cool down and form new stars. This feedback process acts like a thermostat. When the black hole feeds vigorously, it heats and ejects gas, which reduces the fuel available for both star formation and further black hole growth. The black hole essentially regulates its own food supply. Meanwhile, the heating also prevents the galaxy from forming too many stars. Without this feedback, computer simulations of galaxy formation produce galaxies that are far too massive and contain far too many stars compared to what we actually observe. So black holes, despite being a tiny fraction of a galaxy's mass, appear to be essential regulators of galaxy evolution. They help determine how big galaxies grow, how many stars they form, and what they look like. This is why astronomers talk about black hole galaxy coevolution. The two influence each other's growth throughout cosmic history. Research from 2024 and 2025 has shown this in more detail. When black holes at galaxy centers activate and start feeding, they launch outflows of gas that can travel across the entire galaxy, heating material and suppressing star formation far from the center. Observations show both hot gas moving at thousands of kilometers per second and cooler gas clouds being pushed along. The cooler gas actually carries more mass, making it more effective at removing material from the galaxy. Let's return now to the deep connections between black holes, thermodynamics, and quantum mechanics, because this is where some of the most profound mysteries lie. We talked earlier about black hole entropy and how Bekenstein discovered that black holes have entropy proportional to their event horizon's area. But what does this actually mean? Entropy, in physics, is related to information. A system with high entropy is one that could be in many different microscopic states while looking the same macroscopically. For example, a box of gas has high entropy because the molecules could be arranged in countless different ways while still giving the same pressure and temperature. The entropy is essentially counting how many possible arrangements there are. For a black hole, the entropy is enormous. A black hole with the mass of the Sun has an entropy of about 10 to the 54th power, measured in fundamental units. That's vastly more than the entropy of the Sun itself, even though the Sun is a huge ball of hot plasma. This huge entropy suggests that black holes have an enormous number of possible internal states, even though from the outside they look simple, characterized by just mass, spin, and charge. But here's the mystery. Where are all these states? What are the microscopic degrees of freedom that account for a black hole's entropy? In normal matter, entropy comes from the possible arrangements of atoms and molecules. But inside a black hole, according to general relativity, everything has collapsed to a singularity. There's nothing there to have different arrangements. This puzzle is one of the main motivations for string theory and other approaches to quantum gravity. String theory, which proposes that fundamental particles are actually tiny vibrating strings, has had some success in explaining black hole entropy for certain special types of black holes. The strings and brains in the theory can be arranged in many ways, and if you count those arrangements, you get exactly the Bekenstein-Hawking entropy formula. This was one of string theory's early triumphs and suggests it's on the right track, even though the theory remains incomplete and unconfirmed. The holographic principle takes these ideas even further. According to this principle, all the information about what's inside a volume of space is actually encoded on the boundary of that space. It's as if the three-dimensional reality we experience is actually a projection from information stored on a two-dimensional surface, like a hologram. This strange idea comes directly from studying black holes. Since a black hole's entropy is proportional to its surface area rather than its volume, it seems like the black hole's information is stored on its event horizon. Physicists Gerard 't Hooft and Leonard Susskind generalized this. Perhaps any region of space works this way. Perhaps the entire universe is holographic. There's even a precise mathematical realization of this called the ADS CFT correspondence, discovered by Juan Maldacena in 1997. This shows that certain theories of gravity in a curved space are exactly equivalent to certain quantum theories without gravity in one fewer dimension. A three-dimensional universe with gravity is mathematically identical to a two-dimensional universe without gravity, just described differently. If this is true, if the holographic principle applies to our universe, then in some deep sense, our three-dimensional reality might be a kind of projection from information encoded on a distant two-dimensional surface. We might be living in a hologram without even realizing it. This sounds like science fiction, but it's taken very seriously by theoretical physicists as a possible hint about the true nature of reality. These ideas connect to another puzzle called black hole complementarity. This is a proposed solution to the black hole information paradox we mentioned earlier. The paradox is this: when something falls into a black hole, what happens to the information about it? General relativity says it's lost forever inside the event horizon. But quantum mechanics says information can never be destroyed. So which is right? Black hole complementarity, proposed by Leonard Susskind and others, suggests a radical answer. Both perspectives are right, but no single observer can confirm both at the same time. According to an outside observer, information never actually crosses the event horizon. Time dilation makes it appear to take infinite time to reach the horizon, and the information gets encoded in Hawking radiation that eventually comes back out. But according to an infalling observer, they and their information definitely do cross the horizon and fall to the singularity. The key is that these two observers can never compare notes, because once you cross the horizon, you can never communicate back to someone outside. This principle has been debated and refined for decades. Recent work has raised questions about whether it really solves the paradox. Some physicists have proposed that there might be a firewall of intense energy right at the event horizon that would destroy anything trying to cross, which would resolve the paradox but contradicts the idea that nothing special happens at the horizon. Others think the resolution involves quantum entanglement between the Hawking radiation and the black hole's interior in subtle ways we don't yet fully understand. What's clear is that black holes are forcing us to fundamentally rethink our understanding of space, time, and information. They're test beds for our deepest theories, revealing where those theories break down and hinting at what a future theory of quantum gravity might look like. Let's bring this cosmic journey a bit closer to home and talk about black holes in our own neighborhood. How close are black holes to Earth, and should we be worried? The good news is that while there are black holes relatively nearby in cosmic terms, they're still incredibly far away and pose absolutely no danger to us. The closest known black hole to Earth is called Gaia Bone, discovered in 2023 using data from the European Space Agency's Gaia satellite. It's located about 1,560 light-years away. That sounds close, and in galactic terms it is, relatively speaking. But to put it in perspective, if you traveled on the fastest spacecraft humans have ever built, it would take about 40 billion years to get there, much longer than the universe has existed. Gaia Bone is a stellar mass black hole with about 10 times the Sun's mass. It's orbiting a normal Sun-like star, completing one orbit every 185 days. The two objects are far enough apart that the star is safe. At the moment, the system is completely stable and dormant. The black hole isn't actively feeding. In a few billion years, the star might expand into a red giant and start losing material to the black hole, at which point the system would become active. But even then, it would be far too distant to affect Earth. In 2024, astronomers discovered an even more remarkable black hole called Gaia BH3, located about 1,900 light-years away in the constellation Aquila. This one is absolutely enormous for a stellar mass black hole, 33 times the mass of the Sun, making it the most massive stellar mass black hole discovered in our galaxy. It's another sleeping giant orbiting an old star peacefully. There are certainly many more black holes lurking in our galaxy that we haven't discovered yet. Scientists estimate there might be 10 million to a billion stellar mass black holes in the Milky Way. Most are dormant and invisible, drifting through space, only detectable if they happen to pass near another star or if we observe their gravitational effect on background objects. Detecting isolated black holes, ones not in binary systems with visible stars, is extremely difficult. But astronomers have developed clever techniques. One method uses gravitational lensing. When a black hole passes between Earth and a distant star, the black hole's gravity bends the starlight around it, causing the star to briefly brighten in a very specific way. By measuring how the brightness changes, scientists can determine the mass of the intervening object. If it's too massive to be anything but a black hole, and is not associated with any visible object, they found an isolated black hole. In 2022, astronomers used the Hubble Space Telescope to detect an isolated stellar mass black hole about 5,000 light-years away using this technique. It was the first time an isolated black hole had been directly detected through its effect on starlight. Future telescopes, including NASA's Nancy Grace Roman Space Telescope, will be able to find many more isolated black holes using this method. But even with millions of black holes in our galaxy, they're spread across a huge volume of space. The Milky Way is about 100,000 light-years across and a few thousand light-years thick. That's an enormous volume. The chances of a black hole wandering close enough to our solar system to cause any problems are incredibly tiny. We're far more likely to be affected by nearby stars going supernova, and even that risk is extremely small. Some people have worried about whether black holes could be created artificially in particle accelerators like the Large Hadron Collider at CERN. The LHC smashes protons together at enormous energies, and some theories involving extra dimensions of space suggest that at high enough energies, tiny black holes might form. But even if this were possible, and there's no evidence it is, these microscopic black holes would be completely harmless. Any black hole small enough to be created in a particle collider would have an absolutely minuscule mass, perhaps a few thousand times the mass of a proton. According to Hawking radiation, such a tiny black hole would evaporate essentially instantly in about 10 to the minus 27 seconds. That's a decimal point, followed by 26 zeros and then a 1. It would decay into a burst of ordinary particles before it could interact with anything. In fact, if micro black holes could form at LHC energies, similar black holes would be constantly created by cosmic rays hitting Earth's atmosphere. And clearly that's causing no problems. Experiments at the LHC have specifically looked for signs of microscopic black hole production and haven't found any, suggesting that if extra dimensions exist, they're not configured in the way that would allow black hole formation at these energies. The idea of creating black holes in the lab remains in the realm of speculation and far future science. Looking to the very far future, we can ask, what will happen to all the black holes that exist today? We've touched on this, but let's explore it more deeply. The universe is currently in what might be called its stelliferous era, the age of stars. Stars are being born, living, and dying. Galaxies are bright with starlight. This is the universe we know. But this era won't last forever. Based on our current understanding, star formation will continue for perhaps another trillion years or so, but eventually, the universe will run out of the hydrogen gas needed to make new stars. The last stars will form, burn their fuel, and die. White dwarfs, neutron stars, and black holes will be the only remnants left. From about 1 trillion to 100 quintillion years after the Big Bang, we'll be in what's called the degenerate era. The universe will be dark and cold, populated only by these stellar remnants. Gradually, through gravitational interactions, objects will either fall into the supermassive black holes at galaxy centers or be ejected from galaxies entirely. Galaxies themselves will gradually dissolve. By about 10 to the 20 years, galaxies as we know them will no longer exist. Most stellar remnants will have been swallowed by black holes or ejected into intergalactic space. Black holes, particularly supermassive ones, will be the dominant structures. This begins the black hole era. But even black holes don't last forever. Through Hawking radiation, they slowly evaporate. We've mentioned the timescales before, but they bear repeating because they're so staggering. A black hole with the sun's mass would take 10 to the 67 years to evaporate. The supermassive black holes at galaxy centers might take 10 to the 90 years or 10 to the 100 years. To understand how absurdly long these timescales are, consider this. The universe is currently about 14 billion years old, or about 10 to the 10th years. Written out, that's 10 billion years. But 10 to the 67 years is a 1 followed by 67 zeros. It's a trillion times longer than the universe has existed so far. and 10 to the 100 years is a trillion times longer still. During most of this time, the universe will be unimaginably empty and dark. Black holes will be scattered across ever-expanding space, slowly radiating away their mass. The temperature of these black holes is inversely proportional to their mass. Stellar mass black holes have temperatures of only about a billionth of a degree above absolute zero. Supermassive black holes are even colder, with temperatures far below the temperature of the cosmic microwave background radiation that currently fills space. But as a black hole evaporates and loses mass, it gets smaller, and its temperature increases. A shrinking black hole evaporates faster and faster in a runaway process. In its final moments, a black hole that has been slowly evaporating for eons would suddenly accelerate its evaporation. In the last fraction of a second, it would release an enormous burst of energy. A black hole in its final second of existence would have a mass of about 228 metric tons, about the mass of a large building, compressed into a region smaller than an atom. Its temperature would be about 10 trillion degrees, hotter than anything in the universe today. In that final second, it would release about 5 times 10 to the 22 joules of energy, equivalent to about 5 million megatons of TNT, the energy of 1 million powerful nuclear bombs, all released from a point in space. This final explosion would be spectacular if anyone were around to see it. Particle physicists would love to observe a black hole's final moments because it would reveal how quantum gravity works. But by the time the last black holes are evaporating, the universe will be so old, cold, and empty that there will almost certainly be no one there to witness it. After all black holes have evaporated, probably by around 10 to the 100 years after the Big Bang, the universe enters what's called the dark era. Nothing interesting happens anymore. The universe consists only of a thin, cold soup of elementary particles and radiation, all at essentially the same temperature, just above absolute zero, spreading ever farther apart as space continues to expand. This is heat death, the state of maximum entropy. No stars shine, no black holes exist, no structures remain, no energy is concentrated anywhere. Everything has reached equilibrium. The universe becomes a vast, unchanging void that simply continues to expand forever, growing ever colder and more dilute, approaching but never quite reaching absolute zero. This fate seems bleak, but remember the timescales involved. Humanity has existed for perhaps a few 100,000 years. Recorded history spans only a few thousand years. The entire era from the formation of the first stars until the evaporation of the last black holes represents such a tiny fraction of the universe's total existence that it's essentially zero. Almost the entire history of the universe will be spent in that dark, cold, empty state. Yet even this might not be the absolute end. Some physicists speculate about what might happen on even longer timescales. Could quantum fluctuations eventually create new universes? Could there be spontaneous transitions to new vacuum states with different laws of physics? Could some form of information or structure persist in ways we haven't imagined? These questions take us beyond current science into speculation. What we can say is that black holes will be the last major structures to exist, the final monuments to the era when the universe was young, bright, and full of stars. They'll outlast everything else by factors almost too large to comprehend. In that sense, learning about black holes isn't just learning about exotic objects that exist now. It's learning about the objects that will dominate the universe for almost its entire existence. Black holes also hint at physics beyond our current theories. Every black hole is a place where general relativity and quantum mechanics must somehow work together, yet we don't have a complete theory that combines them. Developing such a theory, often called quantum gravity, is one of the great goals of theoretical physics. Several approaches are being explored. String theory, which imagines particles as tiny vibrating strings, is one possibility. Loop quantum gravity, which treats space-time itself as made of discrete loops, is another. Other ideas involve modifying either general relativity or quantum mechanics in subtle ways. Some physicists think the answer might involve entirely new concepts we haven't imagined yet. Black holes provide clues. The fact that they have entropy and temperature suggests deep connections between gravity, thermodynamics, and information. The holographic principle suggests space-time itself might emerge from something more fundamental. The information paradox tells us that at least one of our cherished principles must be modified. Recent work has shown that black holes might even cause quantum superpositions to collapse into definite states. A particle in a quantum superposition is in multiple states simultaneously until something measures it or interacts with it, causing it to choose one state. Physicists discovered in 2023 that the mere presence of a black hole's event horizon causes nearby superpositions to decohere, to resolve into definite states, even without any conventional measurement taking place. It's as if the horizon itself is observing the quantum system. This connects to an old idea by physicist John Wheeler about a participatory universe where observers play a role in bringing reality into being. Black holes, in this view, are cosmic observers, their horizons watching quantum states and collapsing them into reality. Whether this is the right interpretation is still debated, but it shows how studying black holes continues to reveal unexpected connections between different areas of physics. In a sense, every black hole is a laboratory where nature is running experiments in quantum gravity, experiments we could never perform ourselves. By observing black holes carefully, measuring their properties precisely, and studying the gravitational waves they produce when they collide, we're reading out the results of those natural experiments. We're learning what happens when gravity becomes strong enough that quantum effects can't be ignored, and quantum systems become massive enough that gravitational effects dominate. This is why black holes remain at the frontier of physics, even though they were predicted more than a century ago. They're no longer just theoretical curiosities. They're real objects we can observe and study, and they're teaching us about the fundamental nature of space, time, matter, and information. They're bridges between the cosmic and the quantum, between the largest scales of the universe and the smallest scales of reality.